I've been doing a little bit of thinking lately about the scientific method, and I just feel like first of all, the way the word science is used in our culture, it's spread to such a wide range of things and used in such a wide range of contexts that sometimes the word actually becomes meaningless, which is unfortunate. And I also think that it just occurred to me recently that the way that I remember the scientific method from school, I don't even remember now whether it was elementary school or high school, um, it's just not quite. It doesn't give the right thought uh, about what the scientific method really is or what it should be. And so that's why I've titled this "The Scientific Method with Teeth." It's not so much really for me to say that the way that the scientific method is usually explained is incorrect or invalid or is not real science. That's not so much my point, but I do want to say that sometimes there's different ways of doing science that give different amounts of weight to the results, okay? And so I want to talk about what I feel is when the scientific method is done in the best way that gives the most weighty results, the most meaningful, significant, trustworthy type results that also give you the deepest understanding of reality. So if you just Google the scientific method, you'll get something close to what I have over here. So sometimes they lay it out a little nicer, make it a little more fancy, but the basic idea is still the same. So they say, you start with something in reality, you observe it, you come up with some questions. Then this person included that you research, or you try to just, think about and try to study and understand what you're observing. You come up with some hypothesis, you test your hypothesis through experimentation, analyze your data, report your conclusions, and then repeat if necessary if you need to alter or adjust or improve your hypothesis in any way. So, again, I'm not trying to say that that's wrong or even that that would be bad to do. I think that that is good to do, but sometimes the process can be a little a little more specific than that. So I want to describe that. And um, basically, what I'm going to do is I'm going to take this hypothesis section, which I think is almost glossed over in this short little thing, and I'm going to say that this is the most important chunk, the most time consuming, and one of the most important. And then the second is test through experimentation. And then I'm going to say the rest of it is either a given or is insignificant or it doesn't have to be done in the order that's written here. Uh, so first of all, observations, questions. You don't actually have to start there. I mean, you can, but you don't have to. And obviously, observations need to be done, and that kind of goes hand in hand with experimentation and with producing the hypothesis. I almost think it goes without mentioning, or that it should just be like a subset of the other two. Research, to be honest, is unnecessary. It's just a good idea because we have so many years of human history behind us that research is often good. But if you were starting out from the beginning, you wouldn't even have research. So this one is unnecessary. Analyze data. That's also super important. Yeah, so maybe I'll check mark that one too. And and then reporting conclusions, to be honest, is unnecessary. It's necessary from a practical standpoint, but you're still doing science if you don't report your conclusions to anybody. And repeating, that doesn't really need mention, to be honest. This is really just a part of tweaking your hypothesis and experimenting to test your hypothesis. So, yeah, so let's define hypothesis because I really think this is the one that gets glossed over. And I just don't think that you can just do it the way it's written here, and you can have a hypothesis that is just as it sounds. It's just a hypothesis about reality, and you can call that science, but you're going to get into a distinction between the soft sciences and the hard sciences. And I'm not trying to say the soft sciences are not valid, but I'm trying to say that there is a distinction. That's why you can say hard science and soft science because there is a legitimate distinction. And so I think that in this scientific method with teeth that I want to talk about, hypothesis should actually be mathematical modeling, or to be more specific, differential equations. The vast majority of the time, that's what it is. And Yeah, so we're going to say hypothesis. When it says hypothesis, what we should be thinking is mathematical modeling. Which is often done with differential equations. I don't suppose that it has to be, but right. I'll just abbreviate it, differential equations. Okay, so that's important. And then the next part, number 2, is experimentation. And then actually I should include 3. I wasn't going to initially, but 3 is really where a lot of the science is done, is when you analyze and try to understand. And I'm going to say it's not just analyzing your results or analyzing your experiment. You analyze both, actually. You analyze your experiment and you analyze your differential equation. So this is really the core of the scientific method. And once again, the main thing that I want to say is that the hypothesis section in the yeah, I'm just going to say it, the best forms of science, the hypothesis is some form of mathematical underpinning for your hypothesis. Like your hypothesis is underpinned through mathematics. And so let me give an example of what this would look like then. So let's say that I'm going to pick an easy one, obviously. So let's say that we had this object falling, right? And we happen to, when Newton had this, somehow he came up with this: the sum of the forces equals mass times acceleration. And so let's say that if we want to take and model this object falling, well, we could just say, so one mathematical model is force equals mass times acceleration, and so if we wanted to find the acceleration of this object, let's just say that that's where we're going. Or actually, let's say that we're trying to find the velocity of this object, right, at any point in time. So we would say, see, I didn't plan this out ahead of time. I'm going to want to say, so force equals mass times acceleration. So on the left-hand side, I want to have an equation that represents the force. So dv over dt equals mass times g, because we have elsewhere calculated g. Let's see, so we can cancel out our masses. Now we could take the integral of both sides. Derivative velocity respect to time. Sorry, not yet. Equals g, multiply both sides by dt. So on this side it cancels. dt is technically still a vector. Now we have dv equals, I'm going to drop the vector notation for the moment, just because I happen to know it's not going to, we don't need to pay attention to it right now. If you take the integral of this side, take the integral of this side, you're going to find that velocity with respect to time equals v times g, no, sorry, t, whoops. We'll say g times t plus c, where trying to be a little quicker here, so c would end up being the initial velocity. So let's say initial plus, normally you'd often see this written as acceleration times time. It just so happens if we're near the center of the earth, acceleration is g. So I sort of sloppily derived what you would recognize as a formula that's often used. And so this formula really follows this hypothesis part of the scientific method was just completed. Now you would have to take this and go test some falling objects and see, this was supposed to be a 0, does the initial velocity plus the acceleration times time, does that give you your answer? And you'll note from reality that according to this equation, it's not perfect, because as the object, it doesn't mean that it's like wrong, because mathematics and science is more about making something useful than making it correct, like purely correct. I think pure truth is always the goal, but is more or less unattainable. And so math and science is to lead us closer to the pure reality, and we should have an understanding that most of the time the pure reality, the true deepest understanding of things, is really just outside of our grasp, to be honest. So anyway, yeah, so now you could take an object, you could drop it, but you'll notice that according to this, as this object right here falls, it will keep accelerating forever. There's nothing in here that says that it stops accelerating. And if you do some experiments, you'll find that that's not true. If you drop something from 10,000 feet up in the air, it'll accelerate until it reaches what's known as terminal velocity, and then it'll start to slow down. So in order to fit some terminal velocity, in order to change our mathematical model so that it accounts for that observation, now we need to tweak our mathematical model a little bit. And so I wrote this one down because I don't want to mess it up on my video, but so we have the sum of the forces equals mass times acceleration. So in this case, we're going to take into account two forces, because there's a force acting downward that's causing it to accelerate, but there must be a force acting upward that's causing it to decelerate. So the downward force is force of gravity. Upward force is force of drag. And the force of drag can actually be modeled in different ways depending on the circumstances, because it doesn't have such a universal, one-time, easy to use mathematical representation as these other values do. So what we're going to want to do is just use one that works under the circumstances that we have in mind now, right? So let's say that under these circumstances, so we're going to say, all right, so we have the sum of the forces. Whoops, sorry, I put that in the wrong spot. I think my headphones cut out. All right, so the sum of the forces is equal to the force of gravity minus, I'm going to consider this the positive direction and this the negative direction. So in this direction it's positive, and then this will be the force of drag. So we're going to replace this with this. Mass times acceleration, we're going to say, I'll just write it out this way, equals mass times the derivative of velocity with respect to time. Now, so what we're going to say now is, yeah, we're actually going to end up putting this on the left side, but whatever. So we're going to say that force, we're going to replace this sum force here with this mass times acceleration with this. So mass times the derivative of velocity with respect to time equals force of gravity is going to be m times g. G is technically a vector. Minus, and so we're going to assume that the drag force is proportional to the velocity. So force drag is proportional to the velocity, which means proportional to part really just means that you put a constant there. So I'll just call it K. K times V. So this is what we're going to use for the force of drag. So minus K times V. So now this is a differential equation that models the situation with drag. And what you'll find is this ends up being more accurate and gives a solution that will not cause acceleration to continue on forever. And when you test this under different circumstances, you'll find that this one, it's not like this one is completely wrong. Under certain circumstances, this will give you the right answer. Under other circumstances, it will not give you the right answer. This one will give you the right answer under all the same circumstances as this, plus under some new extra circumstances, so it'll give the correct answer even more often. And you could change this drag force to be more accurate, and then it would give you, it would continue to expand the times when your model is accurate. And so that kind of covers mathematical modeling, the hypothesis part. I covered through talking about it the experiment part. I think in this example, the idea of the experimentation is really intuitive. The analyzing part, so if I cover that for this one, I did a little bit with this one here. If you analyze this one way to do that is to see what happens as time goes to infinity. And you'll see the limit as t goes to infinity of v sub 0 plus at is infinity. And we know from reality that analysis does not fit with reality. When we look at this one, we'll say that dv over dt equal, that's supposed to be a regular d, not a partial, g minus k over m, so I divided through by m, of v. So v is a function of time, the derivative of velocity is a function of time. And now, let's see, how do I want to solve this? So I'm going to use the method that I was just going over. So we want to say dv respect to time equals, let's factor out this one. So first of all, I'm going to factor out a -1 times k over m, which I wouldn't have had to do that because I could have done it different, but this is the way I'm choosing to do it. I'm also going to drop the vector notation just for, so I have a little less writing to do, because we've kind of already taken it into account, and it's not going to end up mattering for the rest of this, what I'm going to do. So now we need to factor out a k and an m. dv over dt equals negative k over m times v, and we're going to have to do minus g. Well, I said I was going to drop the vector notation, then I forgot to do it. So we want to have a mass on the top and a k, arbitrary constant, or coefficient of drag, on the bottom. Now we're going to divide by this on both sides, so we get dv, I'm going to try to remember to drop the vector notation, over v minus gm over k equals negative k over m. Now there's a little trick here. So this is equivalent to the derivative with respect to time, the natural log of the absolute value of v minus gm over k equals negative k over m. Now we can integrate both sides. dt. I'm trying to hurry this up. I was going to make this a shorter video, but I wanted to show the process. So this is going to become, after you end up raising it to a power of e, I guess that's how you say that verbally, minus gm over k equals, this side we have negative k over m plus c. Now we take and we add, sorry, I forgot to raise this to an e, so this is e raised to that because I did that on this side. So if we continue to simplify, and I don't really explain any of it here, trying to just speed through it. C e to the negative k over m plus gm over k. So this is a solution, and if we get rid of that c, we can replace that c with, if we consider that the velocity at time 0 equals v0, which is often the way that it's written, we can simplify this, and we're going to get, I'm almost out of room. Let's try to fit it down here. So we have v times 0 equals v0 equals, zoop, I missed the t there. Shoot. There was a t there. There's supposed to be a t there. That's times t. So we have v0, and so this is going to be negative k over m times 0, so the e is going to go to 1, so this will just be c plus gm over k, and we're going to get that c equals v0 minus gm over k. Now we can rewrite this with the v0, which has some significance in reality instead of c. Bear with me, I'm almost done with this. So we have v velocity as a function of time equals v0 minus gm over k, where k is our drag coefficient, times e to the negative k over m times t plus gm over k. Gm over k. So this is our new mathematical model. So our first mathematical model looked like this, but we saw through analysis that under certain circumstances, through analysis and experimentation, which I didn't do just now, but I'm just telling you that let's pretend somebody did it, they would find what I just said, that in reality our object does not continue accelerating forever as this model predicts. Instead, eventually our model will slow down. Our object falling will slow down as this model predicts until it reaches a terminal velocity. And the terminal velocity will be the limit as t approaches 0. T approaches 0 is going to actually, yeah, anyway, I think that was long enough. So I just wanted to show what the scientific method actually looks like and the importance of mathematical modeling and differential equations. Today we tend to stress the importance of experimentation, which in the past they needed that stressed, but today, because they would just come up with mathematical models and not fit it to reality, but they're basically, the scientific method is about this marriage between the two, between mathematical modeling and experimentation. And I just feel like this word hypothesis, it's just not the same. It's not that it's not science, because you can still call that science, and it's very useful in the softer sciences to do something that's a hypothesis instead of mathematical modeling. And even in some of the harder sciences, sometimes the modeling is not, at least it won't be differential equations, and maybe it's technically not mathematical, but I think that this should be the starting point where we think about the scientific method. This should be our initial starting point for what the scientific method is, and the other ones are the like special use cases there. So yeah, that's my video.